When you close your eyes, and I mean really try to picture a conscious machine, a true artificial intelligence, what is the image that pops into your head? Be honest.
I think for almost everyone, it's some kind of metal person.
Yeah,
Exactly.
exactly. Is it basically a human being, just, made of circuits? Someone like Data from Star Trek or C-3PO?
Yeah.
A robot that talks? Maybe gets a bit confused by our jokes?
And maybe even has hurt feelings. That's the default setting. We have this deep-seated assumption that the human mind is the gold standard of intelligence.
We think we're the Rolls-Royce of cognitive processing.
Of course. So any superintelligence would obviously be trying to copy us.
Right, we assume we're the peak.
Yeah.
But I've got a stack of research here that essentially takes that whole assumption, just crumples it up, and throws it in the trash.
Mm.
We are doing a deep dive today into a paper by Roderick Wallace called On Machine Consciousness.
Mm.
And I have to say, this was a massive blow to my ego.
It is a bit humbling, isn't it?
Yeah.
It really forces you to look in the mirror and see something, well, different.
Humbling is a very polite way to put it. This research suggests that human consciousness isn't some high-end luxury processing system. Wallace argues it's actually a stripped-down, simplified, and debrided version of biological processing.
That's the word.
Yeah. Essentially, he's saying my conscious brain is the light version of a much smarter, older system.
It's a provocative thesis for sure. But Wallace isn't just, throwing insults. He's using very specific information theory and control theory to back all of this up.
Okay.
His argument is that human consciousness isn't designed for maximum complexity or maximum smarts. It's designed for one thing, speed.
And in engineering, you usually can't have both.
You can't. It's always a trade-off.
So we're training smarts for speed. That's the deal. Okay, so here's the roadmap for how we're going to tackle this, because it gets pretty dense pretty fast. First, we need to understand this biological insult, why our brains are actually defined by their limitations.
And then we're going to have to wade into the math, into the informational turn.
Which sounds terrifying.
It sounds heavy, but it's really about looking at the brain like a thermodynamic engine. It helps explain why we think the way we do from a physics perspective.
Okay, we'll break it down, and finally we'll get to the part that actually scares me a little bit, the engineering verdict. If we shouldn't build machines that think like humans, what should we build?
And Wallace suggests something called a multiple workspace machine, something that acts less like a brain and more like an immune system.
And that difference, as we're going to see, might determine who wins and who loses in a global crisis.
It might?
Okay, let's start with the biology. Wallace defines human consciousness with a very specific constraint. He talks about a 100 millisecond time constant. Can you break that down for me?
Yeah, think of it as the refresh rate of your reality.
Mm-hmm.
For you to interact with the world, to catch a set of keys someone throws at you or dodge a pothole while driving, your brain has to process all that sensory data and issue a command within about 100 milliseconds.
If it takes longer.
If it takes longer, you get hit by the keys or you hit the pothole. Simple as that.
So that's our speed limit. We have to be that fast to survive in the physical world.
Correct. But here's the rub. In biology and in engineering, high speed usually requires low complexity. You can't process a massive amount of data instantly.
Right.
So Wallace compares our consciousness to other biological systems, specifically things like wound healing, gene expression, and the immune system.
See, I never think of my immune system as thinking. I just think of it as, biology doing its thing.
You should think of it as thinking. Wallace calls the immune system a multiple tunable workspace. Think about what your immune system is doing right now as you're sitting here.
I'm trying not to.
It's monitoring billions of cells, identifying pathogens, differentiating between self and intruder, remembering past infections from 10 years ago, and coordinating a chemical war on multiple fronts at the same time.
It's a massively parallel system.
Incredibly complex. It's
Yeah.
a cognitive system that, in terms of raw data processing and parallel operation, absolutely dwarfs your conscious mind.
So it's technically smarter than I am.
Oh, absolutely.
Yeah.
But it has one fatal flaw for our purposes.
Yeah.
It's slow. An immune response can take hours, even days, to really ramp up.
Right. If a tiger jumps at me, I can't wait 3 days for my immune system to hold a committee meeting and come up with a solution.
Exactly. If your immune system tried to drive a car, you'd crash before you even backed out of the driveway.
Yeah.
So evolution had this problem. It had these deep, complex, super smart systems, but it needed something that could handle, rapid, immediate physical challenges.
So it built consciousness.
Yes. But to get that 100 millisecond response time, it had to sacrifice all that massive parallel complexity. And Wallace uses a medical term here that I found really striking. He says consciousness is debrided.
Debrided. I looked this up. It is not a pretty word. It's what doctors do to a wound.
It is. Debridement is the removal of dead, damaged, or infected tissue to expose the healthy tissue underneath. It's a cleaning out.
So evolution cleaned out the mind.
That's Wallace's argument. It stripped away all that massive, complex, parallel chatter you find in the immune system just to clear a single streamlined channel.
So consciousness isn't the whole house, it's just the hallway.
It's a spotlight, a very bright, very fast spotlight. But, and this is the key, it could only shine on one thing at a time. This is what creates that tunable neuronal global workspace. The benefit is speed. The cost, however, is inattentional blindness.
That's the tunnel vision effect, right?
Precisely. Because you are a single workspace, a single spotlight, you overfocus. If you are intensely focused on a difficult math problem or even just doom scrolling on your phone, you might physically not hear your spouse talking to you.
Your brain literally gates out that information.
It has to maintain its processing speed. A multiple workspace system, like the immune system, wouldn't have that problem. It sees everything at once.
But hold on, if I'm just this stripped-down single spotlight system, how do I actually survive? If I'm looking at a beautiful flower, why don't I get eaten by the tiger standing right next to it? If I'm so debrided, shouldn't I be dead?
That is where the back brain comes in. Wallace argues that the conscious spotlight is actually pretty helpless on its own. It relies on a partnership with a powerful subconscious AI in your skull that manages hyper-rapid stereotypic pattern responses.
Which is a very fancy way of saying what?
Emotions, reflexes, gut feelings.
So my sophisticated humanity is basically just a screen for a bunch of pre-programmed shortcuts.
In a survival sense, yes. You don't consciously calculate the physics of a falling knife to move your foot. You flinch. That's the back brain. It handles the raw data and just sends a shock signal to your conscious mind.
Wow.
So human consciousness is this weird hybrid, a simplified, fast interface riding on top of a deep ocean of emotional reflexes.
Okay, I'm accepting the insult. I am fast but simple. But Wallace isn't just philosophizing here. He shifts gears in the paper and brings in some really heavy-duty math to prove this isn't just a metaphor. He calls it the informational turn.
This is where we move from biology into physics. Wallace leans on 4 specific theorems, asymptotic limit theorems. Now, we don't need to derive them on a whiteboard or anything.
Thank goodness.
But they're crucial for understanding the constraints of any mind, whether it's human or machine.
Okay, let's run through them. We've got the coding theorem and the source coding theorem.
Right. The coding theorem basically deals with sending messages through noise.
Yeah.
How do you get a signal across when they're static? And the source coding theorem that deals with compressing information, things like grammar and syntax. How do I pack a complex thought into a short sentence?
Okay, compressing data. Got it.
Then you have the rate distortion theorem. This one is key. It calculates how much error or distortion you can tolerate before the message just becomes garbage.
Like streaming a video and it gets all pixelated.
Exactly. How pixelated can it get before you can't tell what's happening? But the big one, the one that really anchors this whole paper, is the fourth one, the data rate theorem.
And this is the one that links information to control.
Yes, this is fascinating because it connects information theory directly to control theory. It explains how a system keeps itself from crashing.
The paper uses a driving analogy for this, which I found totally essential for wrapping my head around it. Can you walk us through that?
It's the best way to visualize it. So imagine you're driving a vehicle on a terrible road. It's twisting, it's full of potholes, maybe there are ice patches. The road is generating topological information.
So the twists and bumps, that's the problem I have to solve.
The road is reality. It's the environment throwing challenges at you. And you are the driver. You're the controller.
Right.
To stay on the road, you have to send control signals, steering, braking, accelerating. The data rate theorem is a mathematical law that states you must send those control signals at a rate faster than the road generates twists.
That makes perfect sense. If the road twists left in 1 second and it takes me 2 seconds to turn the wheel,
You crash. Control fails.
Yeah.
It's a mathematical certainty. Your channel capacity for control has to exceed the rate of instability being generated by the environment.
So, bringing this back to the brain, my brain is the driver and the world is this potholed road.
Yes. And Wallace connects this directly to thermodynamics. He cites Feynman and Bennett to argue that information is a form of free energy. Thinking literally burns energy. It's a thermodynamic process.
So if the world throws information at me too fast,
If the road gets too twisty, faster than your brain can process and control it, your cognitive stability collapses.
This leads to a really strange concept in the paper called groupoids. Now, be honest, when I first saw the word groupoid, I thought of a 1950s sci-fi monster, Attack of the Groupoids.
It does sound like that. But in this context, it's all about how the brain shifts gears. In mathematics, a group usually implies symmetry, things staying consistent. But biological systems, they act in ways where symmetry breaks. The rules of the game change suddenly.
Give me an example of a groupoid in action. How does my brain use these?
Okay, think of a deer in the woods. It's playing the foraging game. It's wandering, it's sniffing, looking for grass. The mathematical rules governing its attention and movement are set to search. It's in one state.
Right.
Then a twig snaps,
It freezes.
and then it bolts. It instantly shifts to the escape game. It's no longer sniffing for food. It is running for its life. The symmetry has broken. The brain just shifted gears like a transmission. These different states, foraging versus escaping, are what he describes mathematically as groupoids.
So consciousness isn't just one smooth, continuous flow. It's actually jumping between these different mathematical states depending on what the road looks like.
Correct. And that transition isn't always smooth. This is where the data rate theorem comes back to bite us. What happens when the road gets too twisty and you can't shift gears fast enough?
This is the section on panic. There was a graph in the paper figure 1, the Yerkes-Dodson graph. It's an inverted U shape. I feel like I've seen this before, maybe in a psychology textbook.
You probably have. It tracks cognition rate against arousal. And you can think of arousal as stress, or even the temperature of the system.
Okay.
As stress goes up, your cognition actually improves. You get sharper. You focus more.
That tracks. A deadline makes me work faster. The threat of the tiger makes the deer run faster.
Exactly. Up to a point. You reach the peak of that inverted U. But if the arousal, the complexity of the problem continues to rise past that peak, what happens?
In the graph, it's not a gentle slope down, it's a cliff.
It is a crash. Wallace calls this the onset of panic. The system doesn't just get worse, it fails catastrophically. The text describes this as a phase transition.
Like water freezing to ice.
Exactly like that. It's not a gradual change, it's a sudden structural snap.
And he uses some really intense math to predict this snap. Fisher zeros, the Lambert W function.
Yes, and we don't need to solve them, but we need to understand what they represent. These are tools from statistical physics, usually used to predict phase transitions in matter, like when a metal becomes magnetic or when water boils. Wallace is applying them to the mind. He's essentially calculating the boiling point of consciousness.
So we have this system, the human mind, that is fast. It's prone to tunnel vision, and it has a mathematical break-at point where it just snaps into panic if the data rate gets too high.
A fragile speedster.
Yeah.
And it all relies on how the network is connected. Wallace talks about the star of stars topology.
Right, that was figure 2.
Basically, for consciousness to even happen, for that global broadcast, your brain modules can't just be randomly connected. They have to form a giant component, a kind of supercluster that talks to itself. If that cluster falls apart because the data rate is too high, you don't just get confused, you lose the ability to process reality.
That is terrifying. Okay, so suppose we want to build an AI. The standard approach is just let's build a human brain. But Wallace throws a massive wrench in the works here with what he calls the cultural caveat.
This is a fascinating detour. Engineers often assume there is one standard human brain to copy, a default human. But Wallace points to studies by Nisbet and others that show human perception is deeply, deeply influenced by culture.
This is the East versus West comparison.
Right. The studies suggest that people raised in, say, East Asian cultures tend to view the world holistically. They focus on the relationships between objects and the background.
Okay.
Meanwhile, Westerners, and particularly Americans, we tend to view the world analytically. We lock on to the most salient objects in the foreground.
So if I show a picture of a tiger in a jungle to a Westerner, they'll say, cool tiger. But if I show it to an East Asian person, they might say, I see a tiger in a jungle.
Roughly, yes. The Westerner might miss major changes in the background entirely because of that inattentional blindness we talked about. We lock onto the object. The East Asian perspective sees the whole field.
But why does this matter for AI code? I mean, can't we just code vision?
Because it implies there is no general relativity of consciousness. There is no single universal equation for how a mind perceives the world. If you code a conscious machine, you are inevitably coding a cultural bias into it. You aren't building a human mind, you're building a Western mind or an Eastern mind.
which means our biases become the machine's limitations. So if we build a Western robot, it's going to have Western blind spots.
Exactly. And that complicates the idea of a standard AI brain pretty significantly.
So this brings us to the ultimate engineering choice. Wallace essentially gives us two paths for the future of AI. Path 1. We build the emotional conscious machine.
This is the Blade Runner path. We try to copy humans, flaws and all.
Is that even possible given how messy we just said biology is?
Wallace says it's actually quite doable. You build a fast, single workspace system, that Spotlight. You give a 100 millisecond time constant, and then you tie it to a backbrain AI that has learned all those hyper-rapid stereotypic pattern responses.
So you basically give it fake emotions. You program it to flinch.
Yes. And you would end up with a machine that mimics a human pretty well. It would be fast, it would have feelings, or at least reactions that look like feelings, and it would suffer from the same inattentional blindness and potential for panic that we do.
But Wallace thinks this is a bad idea.
He questions the utility of it. He calls it the social construction of a problem. We want to build it because we want a buddy, not because it's the best tool for the job. I mean, why build a machine that has the same panic attacks we do? Why would you build a car that gets tired?
Which leads us to path 2, the clever designer.
This is the multiple workspace machine. Instead of copying our stripped-down human brain, Wallace suggests we go back to the immune system model.
The slow but smart system. But wait, didn't we say that was too slow to drive the car?
It was too slow for biology. Cells can only signal so fast. But we aren't building with wet cells. We have high-speed electronics. Wallace argues we can build a multiple workspace system, one that sees everything at once, like the immune system, but make it run at the speed of a fighter jet.
He actually mentions fighter jets as an example of this logic.
He does. Modern fighter aircraft are inherently unstable. To keep them flying, they use voting control systems. Odd numbers of parallel computers that all vote on what the flaps should do.
They don't have a single focus.
No, they are constantly checking everything simultaneously.
So they don't get tunnel vision.
Never. A multiple workspace machine is immune to inattentional blindness. It doesn't have to ignore the periphery to focus on the center. It sees the tiger and the flower and the weather and the path all at the same time.
And this leads to a pretty terrifying conclusion he has about the fog of war.
It is a stark conclusion. Wallace argues that in any conflict scenario, a fog of war, a multiple workspace machine will dominate a single workspace machine every single time.
Because the single workspace machine, the human-like one, will panic.
It will hit that Fisher zero. The environment will generate too much information, the single spotlight won't be able to keep up, and it will phase transition into a crash. Meanwhile, the multiple workspace machine, which sees everything, will just keep processing without a problem.
It's the difference between a cowboy in a shootout and a swarm of autonomous drones. The cowboy has to aim. The swarm just sees.
That's a very apt analogy. The single workspace is heroic, perhaps, but it's mathematically inferior in a high-information environment.
There's a quote in the text that sums this all up. Horses for courses.
It's a British aphorism. It just means you pick the right tool for the job. If you want to haul lumber, don't use a racehorse. And if you want to solve complex, high-speed survival problems, don't build a machine that mimics the limitations of the human brain just because it makes you feel comfortable.
He also says, sure, hogs are smart, but I still like bacon and eggs.
Another aphorism from the text. Just because something is smart, like a human brain, doesn't mean it's the right fit for the task. We shouldn't romanticize our own limitations.
So let's recap. We've learned that our consciousness is a debrided, stripped-down speedster, evolved to be fast rather than deep. We've learned that the math of control theory treats our brains like drivers on a potholed road, constantly on the verge of spinning out.
And we've learned that the future of superior AI probably isn't a digital human, but a multiple workspace entity that functions more like a high-speed immune system.
Which brings us to the final thought Wallace leaves us with. And I think this is the most provocative part of the whole paper. He admits that these superior multiple workspace machines would be incredible, they'd be effective, they would win every war, but
as he puts it, they would be nothing like having the family cat on your lap.
that hits home. The family cat, or a human-like robot, is relatable. It has limitations, it has a single focus. We can understand it, we can bond with it.
Exactly. A multiple workspace machine would be alien. It wouldn't think in a way we can comprehend. It wouldn't have a narrative stream of consciousness. It would just be a vast parallel processing force. It wouldn't be a friend. It would be a force of nature.
So here is the question I want to leave you with today. We are racing to build these superior intelligences. We want them to solve our problems, cure our diseases, maybe even fight our wars. But if we succeed, if we build these immune system style minds that don't share our biological limitations, will we even be able to relate to them? Or are we busy creating something so efficient, so alien, that we become the slow, dumb biology in the room?
It's the ultimate trade-off,
Yeah.
efficiency or empathy.
Something to think about the next time you ask your smart speaker to turn on the lights. Thanks for listening to The Deep Dive.
See you next time.